No volunteers? Logan, would you be willing?
Yeah,
Oh.
but like I'm on my iPad, so.
Oh, you're on your iPad, so you don't have your
Yeah.
computer with you?
No, I do, but like I'm using.
Oh, you're on Zoom on the iPad,
Yeah.
not Zoom on the computer. Okay, so who is on Zoom on the computer? Oh, okay. Well, Hayden, you've already done this. So Chance, good, Chance. You willing to do this?
Sure.
Okay. All right. Share your screen with us so we can see what you're doing. Okay. So I'm going to need to make this bigger so I can actually see your screen well. Okay. Oh, yeah, I can actually see your screen pretty well. Okay. So what's the first thing that we might want to do when we're going to get started on an R script? Anybody?
Libraries?
You want to load in your data?
Okay, so one of these you're going to want to do is you're going to want to load in your data. And because I'm not sure what directory Chance is in, what might we want to do before we load up our data? Okay, Chance, explain to us what you're doing as you're doing it. So just unmute yourself, Chance.
We're getting what my working directory is. Is this the right
Okay,
command?
good.
Then we're going to set our working directory as whatever this is.
Okay, well, you don't have to set your working directory because that is what your working directory is. Is that also where your data file is at?
Yeah, well, I mean, it's in a branch of that. Do I have to go specifically into practice 3? Because I'm in stats, of course, but do I have to go specifically?
Yeah, you would have to then go into practice
Okay.
3. So actually, you don't have to do a set working directory thing at this point. You can actually just go and get your data file. So what you want to do is you want to give your data file a shorthand tag. I usually use DAT as a shorthand for data. And then what you want is the assignment operator. And then what you want to do is you want to read a CSV file in. So read.csv, and then parentheses. And then in quotes, because you're already in your working directory, all you need is the directory down below and then the data file, because you're already partway through that. So you would need a forward hash, then whatever your directory is that your data file is in, which is what, practice 3?
All of that below? Yeah, practice 3.
Yep, practice. And it's going to be a capital practice because yours looks like it's capitalized. And then a forward slash, and then loveit.csv. So you started in a level of the directory above the level where your data is at. So whatever of that path you don't already have in there, you need to add that path. So run that and see if that worked. Okay, let's see.
I was having a problem. I tried to open it a second ago, and it gave me a weird error, so that may be why my file may be different. But
love it. Is that a T? Are those 2 T's? It's hard for me to see.
yes.
Okay, it is. All right, let's see. Go back up to your read.csv line and copy your entire path into there, into the parentheses. So go down to your console. And you guys should be loading in your own data file on your own computers as well, as Chance is working with his.
So you want the entire path here?
Yep, the entire path, and then just paste it in front of practice. Yep, right there. Nope. Well, yeah, you need a forward hash after stats. There you go. And then get rid of that extra forward hash up there. So now try that. Okay, all right, so it did need the whole path. So now raise your hands in the little icon thingy when you have successfully loaded the file on your own computer, on your own console. Logan's got it. Obviously, Chance has it. So you should be scripting along, but of course the path is going to be different for you because your path is different on your computer. And remember, if you need to know what your path is, you can go to where the loveit.csv file is, right click on it, and then get info about it, and it will give you what the path is. And that works for both Macs and PCs. Or if your working directory is already set to the directory that you have there, then all you really need is the data file name, loveit.csv. Hannah, is that a thumbs up? Okay, all right. So Hannah's good. Haley, are you aware of where we're at?
Yes, I'm just trying to figure out where it was on my computer again.
Okay, all right. Well, I want to make sure that everybody has it up on their computer before we move on.
I did the get info and got the whole working directory and put it in. It still didn't work.
Okay, is your working directory in quotes?
Yes.
Are you on a PC or a Mac?
A Mac.
Okay, and you started with hashtag users?
Slash users, yeah.
Yeah, sorry, slash users. Okay. Can you go into chat and type out to me what your path is?
Yeah.
Copy and paste it.
Yeah. And then I had to love that after that, but it didn't work, so I deleted it.
So you did /loveit.csv after that?
Yeah.
Okay, go ahead and put that into your R script again and try running it again, and then show me the whole command line that you have. And it's still not loading it.
No, it says it cannot open file, no such file.
Okay. So go back to your Finder window, go to loveit.csv, actually navigate to loveit.csv, and make sure that that's actually where it's found. I realize you just copied the path into there. Oh, is RScripts applied statistics one folder, or is there supposed to be a hash between RScripts and applied statistics?
No, my folder's called RScripts Applied Statistics.
And loveit.csv is inside of there.
Yeah.
That's bizarro. Okay, Hayden, this is weird. It's going to sound weird. Just close R and open R back up and save that script language and then just plunk it back in there.
Okay.
Because regardless of where you're opening R from, that path should take you to your data file. So Blaine's got his loaded. Haley, do you have yours loaded yet?
No, I'm almost there.
Okay. Hannah already signals that she had hers loaded. What about Jonathan? Did you get your data file to load?
Yeah, I'm just about there as well. Sorry, I'm a bit behind.
Okay.
It didn't work again.
It didn't work again.
Because when I run the git working directory, the console gives me /users/Hayden, but that's it.
No, that's fine. That's fine. That shouldn't matter because that's just where you're. So why don't you try this, Hayden? Run the set working directory code and then put in the path that is the path to loveit.csv, and then try just loading, just try read.csv and then loveit.csv. And when you set your working directory, use get wd to check and make sure that reset your working directory. Okay, Jonathan's up.
It won't even work trying to set the working directory.
That is bizarro.
It says unexpected /.
Unexpected / where? That looks like correct syntax to me. I'm looking at my own path on my own screen. Yeah. Okay. Hayden, just hang with us, and if you can come by later on today, we need to probably figure out what's going on with your R console, because it looks to me like that path should work. So just take notes by hand on the commands that we're going to be running through. Haley, do you have yours loaded up yet?
Yeah, I do.
Okay, all right. Okay, so everybody should have their data file in there. So what's one way we can check to see if it actually did it? So we didn't get an error message except for Hayden. Well, even though we don't get an error message, it's always good to check and see if it actually did what we wanted it to do.
Could you do head?
So you could do head, yep. So do that, Chance. So everybody watch Chance's screen. Okay, you don't need to do loveit.csv because you've given loveit.csv a shorthand. Yep, there you go. Okay, so there's the first 6 lines. We have the stream, we have elevation, we have sulfate, we have a modified sulfate value, we have chloride, and then we have elevation 2. What's another way, somebody else other than Chance, that we can check and look at get a glance at what's in our data file?
Can't you just type DAT? And then
You could, but that would then give you the entire data file, and you don't necessarily want that cluttering up your screen. But yeah, you could do that, and it would give you the entire thing. What else could you do? One of the things that the head command doesn't give you is it doesn't tell you what kind of data are in each of these columns. What command can we use to figure that out? And we can do it for all the columns all at once.
we do the structure.
Yep, str, structure. So we can do str.dat. And one of the things, so Chance just did this, and one of the things that you can see is that it tells you that this is a data frame. It's got 39 observations. It's got 6 variables. The variables are stream, elevation, SO4, SO4 mod, chloride, and elevation 2. It tells you that stream is a character, elevation is an integer, SO4, SO4 mod, and chloride are all numerical data, and elevation 2 is once again a character. And so we know that all of the data that it read in are being treated in the way that we expect them to be treated, because stream are actually the names of streams. Elevation is a character data that basically tells you whether it's a high elevation site or a low elevation site. And then all of the other things are some form of numerical data. It's either integer level data or numerical data. So that's good. That's all we really need to do. So now what we might want to do is we might want to verify for ourselves that the low elevation sites are below the average elevation and the high elevation sites are above that average elevation. How would we go about finding out what the average elevation of this data set is? What's another word for average? Mean. Okay, thanks, Hayden. So we would type in mean, and then we want to calculate what the mean of elevation is. So how would we tell R to do that? We want it to take the average of the column elevation in the data frame DAT. Yeah, good. So if you look at Chance's screen, you see that he has told it to give you the mean of data frame DAT $ column elevation. And when you get that, he ran it, and you can see that it gave him a mean value of 535 feet. I think it's in feet. It might be feet or meters. I don't recall for this data set. So I'm going to give you a command that we haven't encountered yet. We've done mean before, but capital view, VIEW, and then the data frame. Type that in. View DAT. Now I sound like a Saturday Night Live character. Now, one of the things that you'll see is that it's opened up a new tab in your workspace up here, and it shows you the entire data set. But rather than it cluttering up your workspace, it actually just opened it in a new tab, so it's kind of out of the way. Now go down to where the boundary is between high and low. So go up a little bit. Yep, there. And see if that cuts off at between 530 at 535. So you see that Kelly Hall and Halcott. Kelly Hall is at 533 and Halcott is at 555. So the high and low divisions are actually made between sites that straddle that average. So we know that high and low are correct. So now go and click back on Untitled 1. Okay, and since it's labeled Untitled 1, maybe one of the things that you want to do is take this time to save that as something that you'll remember, so that if something happens catastrophically, you don't lose your work. This is usually when I name my my files, because it's the first time that I actually look at my data in view, and then I recognize that my tab upstairs, up in the tabs, doesn't have a name, and so I'm like, oh, I should save my work. So we know what the mean is. One of the things that we might want to do is we might want to get an idea of what the distribution of the data look like before we start playing around with it, just to see if it kind of looks like it's normally distributed and things like this. How would we get a distribution of the data? If we want to make a histogram, what do we use for making histograms? We've done this before also. When you wanted the mean, what did you type?
Hist.
You typed mean. So start typing histogram, but go slow, right? So there you go. What does hist do? Hist basically is a generic function that gives you a histogram. So just go hist, and now you need to tell it what you want to make a histogram of. You want a histogram of the elevation column within DAT. No, I'm sorry, not elevation, sulfate rather. We want to look at sulfate because that's what I asked you to do the thing for. And then after that, do a comma. So that gave you a histogram, but you see that the histogram is not particularly well divided. So after you define what column you want it to make a histogram of, put a comma, and then put like breaks equals 15. And this breaks your data up into more bins that it's putting the data into. Oh yeah, so that gives you a little finer grain thing. Go up and do breaks equals 25. And that divides it up even more finely. And there's going to come a point where you divide it up too finely and you start getting these big gaps in your distribution. But this is a quick and easy way to see, yeah, go, okay, do that. Yeah, see, that's too far divided. Yeah. And one of the things that you'll notice, go over to the pane with the plots, and you see that there's an arrow in the upper left-hand side. So cycle back through, you can, and then watch what happens to the frequency, the y-axis. It's changing in terms of the number of observations that are in each bin. As you have fewer and fewer bins, there are more and more observations in each bin. So you'll see that now there's only, yeah. So scroll back to like the first one that you generated, all the way back. Yeah, so in that one, the tallest bin had 15 observations in it, and that's because you're dividing up your x-axis scale into a relatively few number of bins that you're putting data into. So good. How are you guys doing? Is everybody on task? Okay, good, awesome. So one of the things that I've used for you, but I didn't explain it, was a function within a package. So I think you already have this in your list of available packages. So try and load the package rmisc. Okay, so Chance had it, which probably means all the rest of you had it. Raise your hand when you've loaded rmisc. Okay, what about the rest of you? Oh, Hayden, you got rmisc to load up. Okay, okay. Did you ever get your data files to load up? Oh, you did. Oh, good. What was the problem?
Can you hear me? Is it scratchy?
Yeah, I can't hear you.
I just went down to the files section on R, and then I clicked on Love It and clicked import data set and then copied the directory from that. But it was the exact same as what I had put, so I don't know.
Okay, that's weird. Okay, all right. So good job. Well, I'm glad you're with. So you're caught up with us? Oh, good, good. So rmisc is a weird package in R. It actually stands for R miscellany. And when a person writes a function, one of the things that happens is that if that function gets used a lot by people because people are finding it useful, it oftentimes will then get absorbed in some larger package. So there is a function within the rmisc package called summary SE. And this summary SE function used to be a function back when I first started working with R that you just had to have stored somewhere, and you would copy this whole function and plunk it down into your script. Then you would run that function, and then once you had that function run, you could then call that function up. And then finally, it just got thrown in this kind of miscellaneous pile of useful R statistical functions. And so now it's in a package, so whenever you want to use it, all you have to do is call up the rmisc package and use it. So what I want you to do is, Chance, type in summary SE. It's a lowercase s and an uppercase SE. No, summary SE. Okay, so now look at what it's telling you. It's telling that you need a data frame, and it's telling you that you need group vars, and it's telling you that you need measure var. So there's three crucial things that you need. You need data equals data frame. You need measure var. Whoa. equals the measure variable, and group vars equals whatever the grouping variables are. And so that's the syntax, and you get that syntax from looking at that yellowish box. So you've got data equals that, that's good. So then measure var equals, oh, and you're using tab complete, good, that's a good habit to get into. And in this case, the measure variable that we want to calculate for is SO4, the sulfate levels, because that's what you calculated from Wednesday. And then comma, and then group var. Yep. And notice how measure var is singular and group vars is plural. And it's because you can actually have more than one grouping variable. In this case, we're only going to have one grouping variable, but that grouping variable is elevation 2. Now, it's going to just run this when you run it, but you might actually want to save this as something. So save this as, just name it whatever you want to name it. Oh, okay, sure, go ahead. So run that and see what it gives you. Innovation 2 not found. Go run structure again. Line 9. Oh yeah, okay, so you're also going to need to then put quotes around SO4 as well. I always forget the quotes thing. And this is the problem with open source software. Sometimes you have to put your variable names in quotes and sometimes you don't. And I forget that in summary SE, you have to do that. So now when you run data 1, it should just give you the output. Okay, we'll pause here. Raise your hand either in the participants tab, in the responses tab, or on camera when you actually got that to work. Cool, awesome. Can I see everybody? Let's see, who am I missing? Okay, Jonathan, did you get that to work?
Yes, I did.
Okay, cool. All right, so let's look at this output. It's basically telling you, yeah.
Oh, sorry. It ran an error for me. It said unexpected string constant in data 1. That's all it says. Unexpected string constant.
That's weird. Did it give you this output?
No, it didn't give me any output.
Didn't give you any output. Copy your. Can you copy what your summary SE data set your summary SE command looks like in the chat so I can look at it?
Yeah, I'll put it in the chat.
Yeah. Chance, the next thing that we're going to do is we're going to make a graph of these data. So start thinking about how we start off making a graph. while we troubleshoot Blaine here for a minute. Blaine, I haven't gotten anything in my chat.
Yeah, sorry. I went to send it and it didn't send for some reason.
Okay. And the rest of you can start thinking through graphing as well. And if you need to, you can go and so what we're going to want to do is we're going to want to plot the means and the 95% confidence intervals. So that's what you need to be thinking about. And we have graphs from other things. Okay, so Blaine stuff is coming through. Oh, your assignment operator is an underscore, not a dash, Blaine. Can't hear you, you're muted, I think.
In my computer, it doesn't have it as an underscore though. That's what's funky. When I copy it from my Mac, from my PC to my iPad, that's what I'm having issue. So I'm having to literally like hand write it out because I can't.
That's
it's
fine.
not. Sorry.
That's fine. No, that's fine. Are you using option dash when you do the assignment operator? Are you on a Mac, Blaine?
No, I'm on a PC.
Somebody on a PC remind me what the operator, the keystroke shortcut is for the assignment operator? No PC user is going to rescue me?
Unexpected string constant.
What's that?
I just don't understand what it keeps giving me the same thing. Unexpected string constant.
Yep. So alt dash is what it is in PC land. So try alt dash for your assignment operator just on a lark. And then of course I can't see the rest of your command line there. All I have is data one and the assignment operator.
Yeah, it didn't change anything. It still had it as the same.
Okay. All right. Yeah, and I can't help you if I can't see the rest of your command that you have for running summary SE. And you're working on your computer and you're doing Zoom on your iPad? Is that a yes? Pick up your iPad.
Yes. Okay.
And show me your screen.
All right.
Would you like me to stop sharing so you can get full screen, or?
No, I can probably see his screen well enough if he just shows it to me.
No, I'm not wanting to share my screen.
What's that?
I don't want to share my screen on this.
You,
how do I?
no, just pick up your iPad and put the camera in front of your screen. Oh yeah, so now I can see your. Oh, you have two quotation marks after SO4.
Oh my gosh, I do.
Try that.
It still says error in if empty data.
Show me your screen again. Then let me get it big enough on my screen so I can see it. All right. Okay. Your data file is not called data. Your data file is called dat.
Oh, it is. So data would
equals dat.
Okay.
Yeah, you need your data frame name there. Okay. And before you execute that, let me see the rest of your command.
I went ahead and ran it. It went ahead and ran.
Okay, all right, good. All right, then let's go back to Chance.
Thank you.
All right, cool. So Chance has already gotten started. He's loaded up ggplot2. So now Chance, or anybody else for that matter, what's the strategy going to be for making a graph? Well, first of all, before we do that, let's look at the output from running summary SE. It gives us elevation 2, and it shows us that there's 2 levels. There's a high elevation, a low elevation. It tells us that there are 20 observations in the high and 19 observations in the low. The SO4, that's the average value for sulfate in high elevation sites and low elevation sites. So high elevation sites have less sulfate than low elevation sites, which have higher levels of sulfate. And then SD is the standard deviation, SE is the standard error, and CI is the interval for the confidence interval. It's 2.09 above and 2.09 below. Check your hand calculations and see if your hand calculations match up to these calculations that R has done. And if they do the little raise your hand thingy in Zoom, in the response or reactions to Zoom. Blaine's matched, Logan's matched. Jonathan matched, Chance matched. Haley, Hannah. Okay, Hannah. Okay, good. Okay, good. So one of the nice things about homework in this class is after you've done your homework, if you're working things out by hand, a good thing to always do is just plug this stuff into R and see if R gives you the same answer. If R is giving you a different answer, then either you've done something wrong with your hand calculations or you've done something wrong in R, and then you can go through the process of kind of troubleshooting that and seeing what the deal is. Now, whenever we're working with data like this, with means, we have these 2 means. We have a mean for the low elevation and we have a mean for the high elevation. And you might want to make a graph where you're graphing what the sulfate levels are, and you might want to just show that low elevation sites have higher values of sulfate than high elevation sites do. And the way we usually do this is we plot this by plotting the mean average, and we plot the 95% confidence interval. And the point that I was making last time is that when we want to tell if 2 means are different from one another, the question is not, do these confidence intervals overlap? The question is, could this mean have come from this means population? And could this mean have come from this means population? So we're not looking to see if there's overlap in the confidence intervals. We're looking to see if this confidence interval includes this mean, and if this confidence interval includes this mean. And so that's the test for whether or not 2 things are different. So we might want to make a graph that looks like this. So how are we going to do that? What are some ideas on how we can start down that path? So we've loaded up ggplot because we're going to be making a plot. But what's that plot going to look like? What data are we going to reference when we want to plot the means? Are we going to be referencing the raw data in DAT, or are we going to be referencing the summary data in data 1?
The summary data?
Yeah, so we're going to want to be doing summary data. So we need to call up ggplot. So ggplot is the command that we would use. And the first thing in the syntax of ggplot is we reference what data frame we're going to be using. So that would be data 1. Nope. Well, yeah, that works also. You actually, in ggplot, you don't actually have to tell it data. The first thing that it's expecting you to give it is the data frame. So comma, and then what's the next thing that we have to do in ggplot?
Do you have to set the aesthetics?
We have to set the aesthetics. So AES for aesthetics, and then another open parentheses, AES. Yep, there we go. And then for this, we need to tell it what the X variable and what the Y variable is going to be. And so what's the X variable in this plot behind me on my screen, or on my board?
Lows and highs.
What's that?
Your x-axis is lows and highs, correct?
Yeah, but what column is that in? In the data 1 data frame. It's elevation 2, isn't it? Yep. So, but you have to tell it that that's the X variable. So X equals elevation 2. Yep. And so then you need to tell it what the Y variable is going to be. Yep. SO4. Yep. And then you need to make sure that all of your parentheses match. So you need another closed parentheses there. And then do a plus and go to the next line. Now, all we've done is we've told it what data to go and look at and what's the X variable and what's the Y variable. So now what do we want to plot? We want to probably show this as a point, right? How do we get points in ggplot? All of these kinds of things start with the code geom. Type in geom underscore, and then it's going to give you a bunch of, well, okay, you got geom point. It came right up. So geom point, and then let's just leave it open. We won't put in any formatting instructions for now. Do another plus. Actually, go back and get rid of that plus. Just run that and see what it gives you. We'll slowly build up this this graph. So what it's giving you here is it's giving you a graph that shows elevation, and it shows the high elevation sites and the low elevation sites, and it's done high and low because it does things in alphabetical order unless you tell it to do otherwise. But it's just plotted the means. The high elevation mean is 59.27. The low elevation mean is 64.7. And so it's just giving you those 2 points. So other things that we might want to do is we might want to give it error bars. So go back up to the geom point line, put a plus in there, return. Now geom underscore error bar. Okay, run that. So it's telling you geom error bar requires the following missing aesthetics, Y min and Y max. So we have to add some more things to our aesthetics section up there. We need to add what the minimum Y is and the maximum Y is. So do a comma. So Y min is going to be equal to SO4, because SO4 is the average, minus CI, which is the confidence interval in the data 1 data frame. So you can see in your console down there, it says we've got, just leave it right there, you've got elevation 2, high and low in SO4, SD, SE, and CI. What you're basically telling it to do is you're telling it, make a new little variable called Y min that is essentially the average sulfate minus the confidence interval, and that's Y min. So what would Y max be? It would be equal to what?
SO4. SO4 plus CI.
Yep, it would be SO4 plus CI. Good job. Now try running that. So now you have a very ugly looking error bar because they're huge, but it's showing you not only what the mean is, but then it's also showing you what the 95% confidence interval is. So to clean up that error bar, add inside the parentheses for the error bar, width equals 0.05. Now run that. Oh, and now you have some cleaner error bars, but then also those points now look really small. So go up to geom point and just put size equals 3. So we can format what our points and our error bars and things like this look like. So now the points are a little bit bigger. Go to the geom error bar line and add a plus. Now we might want to make this look a little cleaner because there's no line where the X and Y axis are. So what's a command we can use to give it a different theme? A formatting theme. It's one that I rely on a lot. Theme underscore classic. Run that. Yeah, now it's done some things. So your X label and Y label is elevation and elevation 2 and SO4. So one of the things we might want to do is we might want to change how we're labeling things. So how do we change the X label?
Axis dot text dot.
Nope. Nope. That would be for the axis labels. It would be XLab. XLab for the X label and YLab for the Y label. So just put XLab and then in parentheses, in quotations, do elevation capitalized. And then add a plus, and then go to the next line and do YLab. And in this case, SO4 is basically just scientific shorthand for sulfate. Now run that. Okay, good. So what we're doing is we're slowly building up what a graph looks like. And so one last thing that we'll add to this little brief graphing block, do another plus, go down to the next line. And because we often want to have things going from like numerically on your x-axis, you want categorical variables like high and low to kind of follow what our natural tendency is, which is low values on one side and high values on another side, on the right side. So we can use a code that you've seen before, but you probably didn't think about what it was doing to force it to order things in a particular order. And this is scale underscore x underscore discrete. And then in parentheses, you want labels equals, and then the C, because you're concatenating this, sorry, not high, you want to go low, and then high. Is that right? Yeah, try that. No, I'm sorry. It's not forcing it. It's just labeling it. So go back and put them high and then low. Sorry, this is just a labeling. This is just labeling them with better labels than we had before. So now they are capitalized high, capitalized low. We'll discuss later how we can force them to change the order of things. So at high elevation sites, we have lower sulfate than at low elevation sites. And because you can see that this mean does not fit within this confidence interval, and this mean doesn't fit within this confidence interval, chances are those two means are different from one another. They're statistically different from one another. And this idea that two values can be statistically different from one another is different than if those differences have any practical real world meaning. It's just a matter of how does the variability around this mean that is the low mean, how does that variability and the value of the mean relate to the variability and the mean of the high elevation site? So now you're labeling it graph 1. So if you run that, now anytime you type graph 1, it'll just give you the graph. And you can't really see that because it's the same graph. But one of the things you could do is you could use the broom over there in the plot viewer. Use the broom to get rid of all of your previous graphs. Now run graph 1 again, and it should, nope, you don't need, you just need to do it down there, yep. Yeah, so when you type in graph 1, it'll do it. So is everybody able to accomplish this? Give me some indication as to whether you got this done. Okay, all right, good. Nice job, Chance. I'm going to send you out a script that adds an additional thing to this. So Chance, stop sharing your screen. You guys should all save that work that you've done. I'm going to share my screen really quickly with you. So can you see my our environment now? Okay. So let me clean up my spaces here. So this is the plot that Chance just did. I also made a different plot. Sometimes it's useful to have not only the means and the confidence intervals, but it's oftentimes useful to see what the data actually look like. And so I also want you to get across this idea in your head that this 95% confidence interval doesn't refer to the underlying data. You can see that there are a lot of data that fall outside of this range. This 95% confidence interval is a 95% confidence interval of the sample mean. So if we went to these high elevation streams and sampled them over and over and over again, we would get a bunch of sample means. Well, we would expect 95% of those sample means to fall within this interval. If we went to the low elevation sites and sampled this population over and over and over again, we would expect 95% of the means to fall within this interval. And so that's almost always going to be smaller, though that is always going to be smaller than the range of the raw data. But it's sometimes useful to see, oh, this average value is being drug upward somewhat by this outlier that we see right here. And so all I've done for this thing is I am plotting the raw data. So I went back to the raw data file and I'm getting it to plot the mean and the error bars using a statistical function within R. So I'm just going about it a slightly different way. But because I'm using the raw data, it then allows me to illustrate the raw data, which I can't do when I'm just referring to the summary data that we generated with summary SE. So summary SE is quick and easy because it gives you these summary statistics about your data that you can then use for plotting. But then when you use them for plotting, you lose access to the original data themselves. And so there are always 12 different ways to do things in R. And depending upon what you're trying to communicate, some ways are just better than other ways for that particular goal at that particular time. So I'll post this so you can see a different way of plotting. And then another plot that I made just for kicks is you can also use ggplot to look at variation, look at these data in other ways, like making a continuous plot of elevation and seeing how elevation is how sulfate is influenced by elevation, and you see this trend going down. We've imposed an artificial distinction between high elevation sites and low elevation sites, but that difference that we then see between high elevation and low elevation sites is due to this correlation between those two variables, the raw data of elevation and sulfate. So as I was playing around with this data set, I did some things beyond what we did in class, but I'll post that so you can kind of play around with those yourself. All right, questions about that? Are you feeling more comfortable with interacting with R? Okay, Chance, you looked a little hesitant. Your facial expression.
I've been using R since last semester. I had data 350, so that's why I was.
Is that the visualization class? Okay, so you're used to, especially using ggplot. Okay, all right. So one of the goals here at the beginning is to get you more familiar with R, getting you feeling more confident with R, so that you're relying on your own scripting skills rather than relying on me to be feeding you scripts, which is why I'm trying to not feed you scripts as much as I'm trying to get you to generate things on your own. So, all right. So I asked you guys to go and read your textbook. The section dealing with type 1 and type 2 errors. So I'm going to try and share my little pad here, which I'm finding myself unable to do. It seems like every time I have to do this, I have to log off and log back onto the network. All right, can you guys see my iPad? It says type 1 and type 2 errors at the top. Okay, good. All right. Let me get back to the point that I can see you. Okay, so who can tell me what a type 1 error is based on your reading?
That when you mistakenly reject a correct is null hypothesis.
Okay, so that's a complicated thing. What do we mean when we talk about the null hypothesis? So you started there. Let's go with that. What's the null hypothesis? Well, I erased it. So we had, let's just stick with the stream data for a minute. The sulfate levels in these streams. We have high elevation streams, which had low sulfate values, and we had low elevation streams that had high sulfate values. If sulfate is varying from somewhere down in the 50s to somewhere up in the 70s. Okay, so one of the questions that we might ask about these data is this mean different from that mean? That is actually the alternative hypothesis, which is that sample mean 1 is, in this case, sample mean high is not equal to sample mean of the low elevation streams. So what's the null hypothesis if this is the alternative hypothesis? Well, what's the opposite? If the alternative is that they're not equal, what would be the alternative to that? Hayden, are you talking?
That they are equal?
That they are equal. So this would be the mean of the high elevation sites are equal to the mean of the low elevation sites. So this is the null. The null hypothesis is almost always the hypothesis of equality. And the alternative is always something other than equality. In this case, it could be very general, meaning that they're not equal, or it could be very specific, such that you might hypothesize that high elevation sites have higher levels of sulfate than low, or you could also do it that low has higher sulfate levels than high. But the more general one is just they're equal versus they're not equal. So we're out of time. So we'll pick up type 1, type 2 errors next time. Meet online, because actually there probably won't be any coding at all on Monday, but we'll start into type 1 versus type 2 errors in earnest. So no homework or anything. Have a good weekend. Relax a little bit. Stay warm. It's going to be brutally cold, and I'll see you back here on Monday. All right.
Thank you.
See ya.